Okay. The torque, the net torque on this meter stick, then is the torque due to gravity. Torque due to gravity, we need the lever arm. The lever arm is this distance from the rotation axis out to where the force is applied. So R is half the length of the meter stick, 0.5 meters if we want it. We need the perpendicular component of the force. Well, the force already is perpendicular. That's convenient. So all we need is the force, mg. That right there, the L halves times mg, is the net torque caused by the force of gravity. We're not done though. Torque is a vector, so we need to specify what direction it's in. Now it's okay to go ahead and say clockwise or counterclockwise, that's fine. Or we could say positive z or negative z according to our traditional coordinate system, which is, either way is fine. Which way, if I'm holding it right here, the instant it starts to fall, what direction will the torque be in? Negative z. So it's going to fall clockwise. My thumb's pointing backwards. So we can say clockwise or negative k hat. Either way is fine. So that torque is a vector. The L halves times mg is simply the magnitude of the torque. But then we need the direction associated with it. What's going to happen to that torque as the meter stick continues to fall? It's going to decrease. Why? R is still L halves. The force is still mg. Right. The force of gravity is no longer perpendicular. It has a component that's parallel to the beam and a component that's perpendicular to the beam. It's only this perpendicular component that we need. Okay? So the torque will change as the meter stick falls. The torque gets smaller and smaller and smaller. Where will the meter stick be when the torque is the smallest possible value? Vertical. So what can you tell me about the torque at that point? It'll be zero. Exactly right.
Because it goes that way, it'll be negative.
Well, it'll be opposite what it was, yes. So at this location, when the meter stick is vertical, the force does not have a component that's perpendicular to the lever arm. They're parallel. If they're parallel, then there can be no torque. So at that instant, there is no net torque. That's why objects, as they swing and finally come to rest, will finally come to rest such that the center of mass is directly below the rotation axis. Because at that point, there will be no net torque. So the rotation, assuming there's friction to make it come to rest, the torque will be zero at that point and it will come to rest. It will be in equilibrium. As the meter stick continues swinging on the other side, the direction will change. The torque will, the torque will then be counterclockwise, or positive z, which is why it slows down on the way up and then speeds back up on the way down. So torque. A net torque is required to make an object's rotation change.
Isn't it still traveling in the clockwise direction, so it's still negative?
The angular velocity would be negative, but the torque would be positive. force of gravity this way, it's trying to rotate the meter stick back down. So the torque will now be counterclockwise.
You're talking about the force, not what the stick is actually doing.
Right.
Okay, I was wrong.
So its angular velocity could still be negative. Okay, it could still be clockwise. But the torque would be positive K, which is why it slows down. The same rule applies. If you remember, displacement, velocity, acceleration. If I'm moving this way, but my acceleration's that way, what has to be happening? Have to be slowing down. If my velocity and acceleration vectors are in opposite directions, I'm slowing down. If they're in the same direction, I'm speeding up. So here, even though the meter stick's still rotating that way, its angular velocity is still negative k hat. Its torque is positive k hat. Turns out the torque determines the angular acceleration. And that torque determines the fact that it will slow down as it continues swinging. So what we want to look at here is Newton's second law, basically. How do we apply Newton's second law to objects that are rotating? It's not as simple as simply taking F equals ma. The net force acting on the object will determine the acceleration of the center of mass, but only certain forces can actually produce torques. It's a torque that is required in order to make an object rotate or make it stop rotating. In order to change the rotation of an object, make it start, make it stop, you have to have a torque. Torque is required. Not all forces will produce torques. You got to get that in your head. Okay? Not all forces will produce torques. So just because you have a force acting on an object does not mean that it will rotate. So Newton's second law. Newton's second law, the one we've used so far, the net force is equal to mass times the acceleration. If there was a net force acting on our object, then our object would accelerate. Now it could result in a regular tangential acceleration, meaning our object would speed up or slow down, or it could result in a centripetal acceleration, meaning our object changed direction. We also looked at cases where the net force was zero, where the acceleration was zero. We need to tweak Newton's second law a little bit to make it apply to rotational motion. Number one, rotational motion requires a torque. So we need a lever arm. So I'm going to multiply both sides by a lever arm. Now we're assuming we're looking at just the forces that are perpendicular. Okay? If you want, you can put that back on. Now, as an object rotates, for example, our meter stick, not every piece will have the same acceleration. A is not going to be the same for everything. Pieces farther from the rotation axis will have a bigger acceleration than pieces closer to the rotation axis. So it's not particularly helpful to leave our equation in terms of A, because A is different for everything, and that makes it a little difficult to work with. But every piece of our meter stick will have the same angular acceleration at any given point in time. How are A, regular acceleration, and angular acceleration, alpha, related? Right. I'm going to put that in. So in place of A, I'm putting R times alpha. So basically, I end up with now the way I have this written at the moment assumes all of the mass is located at the same distance away from the rotation axis. That's what this mr squared is implying. Technically, we need to make this a summation of all the individual little pieces of mass times their distances away. This quantity right here, the quantity of all the masses times their radii squared, their distance squared from the rotation axis, this is called the moment of inertia. Or it's also sometimes called the rotational inertia. Now, when we talked about Newton's first law in the first place, the law of inertia, we said an object would stay at rest unless a net force acted on it. An object in motion would continue with a constant velocity unless a net force acted on it. Inertia in that case was related entirely on the mass of the object. When we talk about rotation, the inertia doesn't depend just on the mass, it depends upon where the mass is. Okay? For example, this hammer, it's not really hard, but it's harder to swing this hammer when the head's at the opposite end than to try to swing it this way. It's much easier to swing it this way than this way. Now granted, it's not very useful to swing it this way because hitting it with the handle won't do a whole heck of a lot. But it's much easier to swing it when the head is in my hand versus the handle in my hand. And that's because of where the mass is located. The rotation axis is my hand. That's where the hammer's rotating around, is the middle of my hand. The hammer has a set mass, but when the head is out here, more of the mass is located at a big R. A big distance, well, a bigger distance than if it was here. If the head is in my hand, then R on average is smaller. You can think of the center of mass. R to the center of mass is really small if I'm holding the head. R to the center of mass is big if I'm holding the handle. The moment of inertia is bigger right now than it is with the head in my hand. Smaller moment of inertia, less torque is required to give you the same angular acceleration. The bigger the moment of inertia, the more torque is required to give you the same angular acceleration. That's why it's easier to hold it with the head in the hand than outwards.